Okay, we're live. So today's lesson is basically going to be a little bit of review of some stuff from grade 10 and 11, and a little bit of grade 12 stuff that you haven't seen yet. This stuff pops up in the grade 12 curriculum. First, we're going to talk about division. If I was giving you that divide, you'd probably just basically divide it by factoring, right? If you're looking at this one and you're going, oh, I have to divide these two numbers, but I can cancel those zeros, right? What did you really just do? Well, you just really factored out a 10 from both numbers and then divided 10 by 10 to get 1. And then, of course, dividing a number by 2 is pretty easy. So what's half of 504? Well, half of 500 is 250, half of 4 is 2, so 252, right? Nice and easy. Now, if I give you this one, there might still be some people who want to factor it, because after all, 16 is just 4 2s, right? It's 2 to the 4. I could cut that number in half 4 times. But let's assume that maybe that's more work than I want to do. What's your strategy now? Well, unless you have a calculator on you, your strategy is to long divide, right? So, quick refresher, how does long division work? Well, I ask myself how many 16s go into 50. How many 16s go into 50? If I was counting by 16s, how many would I need? 16, 32, 48, 3 of them. And then how did I get that number? Some of you are like, oh my God, I haven't done this in grade 6. Right? Okay, but do you remember how did I get this 48, right? I went 3 times 16. And then there's a remainder of 2. What's my next move? Yeah, you bring down the next digit. So the next digit here happens to be a 4, so I have to bring that down. 16 goes into 24. Again, let's count by 16. So I'll only get one of them. So 1/16 is 16. 24 minus 16, I got to think about what 24 minus 16 is. 14 minus 6 is 8. Right? Double check my mental math on that. Now, what's the next step? Why would I bring down a 0? I mean, 0 doesn't have any value. Yeah, but it matters because it's a placeholder for the ones place. So I do need to bring it down. So there we go. Down comes the 0. And then how many 16s go into 80? 5. No remainder. My answer is 315. Okay, so is that enough of a refresher on long division? Great, let's do it with algebra now. If you take a look at the second page of this document,
Stand and remove your hats for O Canada and the treaty acknowledgement.
So that document there that I gave you yesterday, or the day before for the guys in the room, the second page has a whole bunch of divides.
With respect the traditional land upon which British Collegiate and Eminent Trail School Division reside. We commit to moving forward in partnership with Indigenous communities in a spirit of collaboration and reconciliation.
And we're back live, and back to, come on, there we go, back here. Okay, so I have a bunch of divides for algebra. Now, obviously, if I had to divide like 1a here, and I honestly don't know if I did this right. I think this is 1a. X squared plus, oh, maybe I'll just go back and look at it rather than make one up. 8x plus 15, there we go, plus 8x, come on, 10. 8x plus 15 divided by x plus 3. This one kind of reminds me of this divide because I'm really going to factor it. I can kind of see just by looking at it, just like I could see, oh, there's common factors in these two numbers, so I can just cancel them out. I can see in this thing that I've got common factors. I know that the top just factors to x plus 5, x plus 3, and then I divide that out. So really, logically, I kind of treat it the same way. This answer is x plus 5. But what happens when you're dividing polynomials and you're kind of in this situation where it's maybe not so easy to see large enough common factors, or maybe not any common factors? Heck, what if instead of 16 this had been 17? Then for sure you wouldn't be looking for common factors, right? You wouldn't see any. So what do you do then? Oh, yeah, undo that. There we go. What happens if, instead of something like that, you had something like, I would like to know what x, come on you, I'd like to know what x cubed minus 2x squared plus 6x minus 12 divided by x minus 1 is. Now, even if I know x minus 1 is a factor, and I don't, do I know quickly what the other, I guess, trinomial would be with an x squared in it that you'd multiply to get that? And I can't just look at it and tell. I need a different strategy than factoring. So I'm going to long divide. Just the same way I long divided with numbers, I can long divide with algebra. So long division with algebra looks like this. Start by basically writing it out the same way. You put x minus 1 here, the thing you're dividing by, and underneath the brackets, the thing you're dividing into. And then you kind of approach it the exact same way we just approached the numbers. You ask yourself, you say self, how many x minus 1s go into x cubed? And don't even worry about the minus 1s, just think about just the leading number here. How many x's go into x cubed? And it's x squared of them, right? You're going to have to multiply by x squared. And then what did you do next when you were long dividing? You multiplied this number by that number, right? That's what I'm going to do again. So I'm going to go x squared times x minus 1, which is x cubed minus x squared. Here's the most common place people make mistakes. What is my next move? Subtraction, correct. Don't forget that you're subtracting a binomial here. Here's what I do to make sure I don't goof that up. I put a bracket around it. You'll notice textbooks almost never do that, but it's so easy to forget that you're subtracting this negative right here, and I don't want to forget that. Okay, so I'm going to actually put a bracket around it. So I have x cubed minus x cubed, and then I have negative 2x squared minus negative 2x squared, which is negative 1x squared. That's my remainder after the first step. Just like in the numbers, I had a remainder after the first step. And what did I do when I was doing the numbers? I brought down the next digit. So what am I going to do here? I'm going to bring down the next term. And now I ask myself, what would I have to multiply x by to get negative x squared? Any thoughts on that? You're going to multiply it by negative x. And then you have to multiply the negative 1 by negative x. And then you have to subtract. See how that's working? And then you just repeat the steps. In math, we call this an algorithm, right? It's a series of steps that gets us to the answer. That's what long division is. It's an algorithm. So negative x squared minus negative x squared cancels. That was the point. And 6x minus x is 5x. And I bring down my last thing here, minus 12. And then how many x minus 1s go into 5x minus 12? Well, the most I'm going to get is I'm going to get 5x of them, or I'm going to get 5 of them. So 5 goes into 5, or 5 goes into 5x minus 12. So 5 times x minus 1 is 5x minus 5. I'm going to subtract that. And there we go. I'm going to have negative 12 minus negative 5, which I guess is negative 7. Now, what do you do with a remainder? Now, the first long division example I gave you was just the numbers kind of worked out nicely. It didn't have a remainder. What do you remember doing with remainders? Well, in grade 7, you probably just went, again, let's say this had been 17. 17 into 50, 40, right? Okay, so 17 goes into 50. It's probably still 3 times, right? Oh, no, it's not, because it would be 2 times now. Oh, I should have picked an easier one. That's 34 and 16. There's the tough one. How many 17s in 164? 10 of them would be 170, so I want to say it's 9. 9 17s, what's 17 less than 170? 153? Let me know if I goof this up. Oh, good luck with that. Who knows their 17 times table? How many 17s in 110? 5, you think? Okay, let's try 5. This does have a nice self-correcting, right? Because if I'm too big, I'll end up with a number I can't subtract here unless I get a negative, right? So 5 17s is 50, and 35, is that 85? So I guess it's 6, so we were too small. 6 17, so 60 plus 42, 102, that's our winner. So what did you do with that 8? In grade 7, you just went, oh, remainder 8. But we can be more sophisticated than that. What do you really want to do with that 8? Divide it by 17. How about you remember that this can be written, the way I had it written originally, in fact, was as a fraction. So my answer is basically a mixed number. There's the way we want to see the answer. And that's what we want to do algebraically. Algebraically, this divide has this answer, x squared minus x plus 5 minus 7 over x minus 1. Get it? The remainder over the thing I'm dividing by, just like I would with numbers. Cool. Okay, you want to try one more? Let's try one more. This one has one extra trick to it. So let's call this example 2. And let's write it down as how many x plus 3's go into 2x cubed plus 5x squared. And I'll say, actually, I'm going to write it down over here. I'm going to write it as 2x cubed plus 5x squared plus 9 divided by x plus 3. So say that was the actual question over here. So this is the question. Now I'm going to start writing it out in my long division form. I've already gotten a good start on it. But I would not just put, don't write this down yet, I would not just put plus 3. Because every term needs to kind of have a place for it. Notice there's a place for the cube, there's a place for the squared. I need a placeholder for x. So that's what I actually have to do. So let's get rid of all this red stuff. And we're going to put a placeholder of 0 x's before we write plus 3. The same way that when I was doing numbers, I had to bring down that 0, even though bringing down a 0 seems pointless. Question?
So is it plus 3 or is it plus 9?
Oh, I'm sorry, that's right. Good eye. Thank you. Okay, I'm ready to divide now. So let's try it again. How many x's would I need, or what would I need to multiply x by to get 2x cubed? I have to multiply by 2x squared, right? 2x squared times 3 is 6x squared. I'm subtracting that. 5 minus 6 is negative x squared. Just like, I know it seems weird to bring down nothing, but I had to do it with numbers too, didn't I? Bring down 0 x's so that I have a place value or a placeholder for the term that makes the algorithm work. How many x's do I need to multiply by to get to negative x squared? Negative x of them. So that's negative x squared minus 3x. Careful, I'm subtracting that. Again, this is the number one place people goof this up. 0 minus negative 3x is, come back to me pen, 3x. And then I bring down a 9. And this one's actually easier than the last one, except for that little trick about the 0 x's, because what do you notice about this one? I don't have a remainder. X plus 3 times 3 gives me 3x plus 9. And this is going to happen to us in this course more often than not. It'll go in and it'll be a factor, because the main reason we're learning how to do this is so that we can find x-intercepts. In grade 11, you, of course, learned how to find x-intercepts for parabolas. What was the one we did earlier? It was x squared plus 8x plus 15. Quick, what are the x-intercepts? Well, I set y to 0, and it's 3 and 5, so my x-intercepts are negative 3 and negative 5. Now, please notice that when I went from this step to this step, what did I do? Like, what was my logic? Sometimes I ask this of students. I go, hey, how did you get from that line to the next line? And they honestly go, I don't know, I just know that that's what I'm supposed to do. You forget logically what you're thinking. Your thinking, this is the thinking, is that, hey, if this is a 0, I have a number times a number, I have to think what x allows me to have a 0, right? Because if you have a number times a number makes 0, well, one or both of those numbers have to be 0. So what x do you add to 3 to get 0? Negative 3. What x do you add to 5 to get 0? Negative 5. this allows us to think in terms of something called the factor theorem. Just going backwards on this, I'll write it down formally. Some people who were trying the worksheet already hit number, is it 6 or 7? Whatever it was, number 7 I think it was. And they said, what the heck's the factor theorem? You kind of already know this. Basically, this is the factor theorem, but backwards. When I was doing quadratics in grade 11, if I know that the function has to equal 0, then I know that, well, if this is a factor, that's a 0. The factor theorem just says this backwards. It says, come back to me, pen. If f of x equals 0 for some f of a, then x minus a is a factor. So let's take a look at number 7. Let me move over to the workbook here. Number 7. Yeah, there it is, number 7. Okay, so let's take a look at 7a. Was it going too fast there?
No, I just feel like we did this one.
Oh, is this the, okay, but you know what? I didn't do it the other class. Remember, their class was 5 minutes shorter. So I'm just going to do 1a again, or 7a again. So sorry, this is a repeat for you guys in the room, but the guys at home didn't see this one. 7a is x cubed plus 5x squared. Plus 2x minus 8. So I would like to factor this. And my first step is, well, I'm going to guess and check. If this factors to whole numbers, you know what I do know? I do know that the factors have to be factors of -8. You can think about why that is. Think about multiplying. If you multiplied a binomial times a binomial times a binomial to get this x cubed, notice those 3 numbers together that are the constants. Like say that you have, I don't know, x plus a times x plus b times x plus c. Those constants a, b, and c have to multiply to make -8, right? So there's no point in trying 7. There's no point in trying 3. Stick to factors of 8. So what are the factors of -8? Well, there's plus or minus 1, there's plus or minus 2, there's plus or minus 4, there's plus or minus 8. And luckily for me, this is an easy one, 7a, it's the first one. They give you a nice easy one first. 1 works. If I plug in 1 for x, I get 1 cubed plus 5 times 1 squared plus 2 times 1 minus 8, and that happens to be 0. Therefore, x minus 1 is a factor. That's what the factor theorem says. The same way that working backwards, if you were factoring a polynomial or factoring a trinomial in grade 11, and hey, x minus 1 was a factor, oh, then I know my x-intercept is 1. We're just doing it backwards. We know the x-intercept is 1, so x minus 1 is the factor. And now that I know x minus 1 is a factor, I can use my new long division skill to find the other factors. So let's run through it one more time. What do you times x by to get x cubed? X squared. 4x squared is the remainder, bring down a 2x. What do I multiply x by to get 4x squared? 4x. And multiply by the -1. And again, when your grade 12 teacher shows you this, act surprised so you don't disappoint them. 2x's minus -4x's is 6x's. Oh, did I do something wrong? Should it be 6x squared? Where did I go? X squared times x is x cubed. 4x times x is 4x squared. 4x times -1. Yeah, that's a mistake right there. No. Sorry. Mulligan. Bring down the 2x. 4x times x is 4x squared. 4x times -1 is minus 4x. No, I didn't do that wrong. Did I minus something wrong? 5. Yes, there it is. Oh, thank you. You see the mistake. See, didn't I tell you that was the most common mistake? And I made it. 5x squared minus, oh, this should be a minus x squared for one thing. 5x squared minus negative x squared is 6x squared. Thank you for noticing that. There we go. Now bring down the 2x. Okay, so that means this is the wrong digit. 6x. Thank you. So 6x times x is 6x squared. 6x times minus 1 is minus 6x. I'm minusing that. 2 minus negative 6 is 8. There we go. Sorry about that. 8 is my final digit up there. 8 times x minus 1 is 8x minus 8. No remainder. And that's how I knew I had a mistake. I kind of knew I had to have no remainder. How come? Because it's the factor theorem. I knew x minus 1 was a factor. It can't have a remainder when I divide it. So I knew that it had to work. And it does work. So now I know that this original thing here, x cubed plus 5x squared plus 2x minus 8, is actually my first factor times this factor. And if I stop there, I'm going to lose a mark. Question? Oh, yes, sorry. All good. Okay, why would I lose a mark if I stop there? Because what did the question want me to do? It wanted me to factor. Am I done factoring? Think back to grade 5. If your teacher said make a factor tree for 24 and you went 3 and 8 and stopped, no, you're not done. 8 has factors, and so does x squared plus 6x plus 8. That factors one more time to plus 4 and plus 2. And what I want you to kind of realize is why you're doing this. You know why you're doing this? Because now, if this had been, say, a function, I know where the x-intercepts of that function are. There's one at 1, there's one at negative 2, there's one at negative 4. I also know that it's a cubic, which means one arm goes up and one arm goes down. And since the a value of the cubic is a positive, that's a positive symbol, not a scribble, then I know that that means that it starts by going down and it ends by going up. I know it can't change directions more than twice because it's a cubic. So it does something like this. And in grade 12, again, oh, and I know this number here is minus 8, right? Y-intercept, set x to 0. So in grade 12, that is something you'll have to be able to do, is graph a cubic, the same way you graphed quadratics for a month back in grade 11. But where you stop in grade 12 is right here. Because, you know, I kind of don't know how high that is or how low that is. I could maybe make a table of values and kind of guess and check it. But how do you find out exactly how high this is or how low that is? That you need calculus for. And that's why this is a skill that we need. We need to be able to get this far. And then in this course later on, we'll be able to go farther and actually find what we call here our local maximum and our local minimum. So that's a calculus skill. So basically, the ability to factor, which you've been doing since grade 10, combined with now you have this new strategy called long division and the factor theorem, together allow you to get this far. So that's what this worksheet's about, is being able to get this far. Because later in the course, we have to be able to find these numbers. Now, somebody always points out, Mr. K, I hate long division. I was never good at it in grade 6. Every once in a while I meet a student who didn't do it in grade 6. Like they just, some places don't do long division for some reason. So they go, there's this thing called synthetic division. Can I do it that way? And the answer is yes. So if you've seen synthetic division and you want to use it, go right ahead. I don't mind. I'm not going to bother teaching it. I'll leave that to your grade 12 teacher. But if you take this worksheet home and you're playing with long division and it's not going well for you, come and see me. Just in 5 minutes at lunch or 10 minutes, I could teach you how to do synthetic division. I will admit I'm actually not that good at it because I learned long division. I like long division. But synthetic division works too. It's just a bunch of steps to memorize that don't make sense on their own. You see, to me, this makes tons of sense because, or this, you know, this strategy here makes all kinds of sense to me. Come on, Pen. Because I grew up doing, I think when I was a kid, long division started around grade 4. Now they've pushed it to grade 6. So you guys don't have as much experience at long division as somebody of my generation would have. But if you'd rather, again, try the long division. If it's just not going right for you and you want to see what synthetic division looks like, come and see me and I'll teach you synthetic division. Otherwise, we'll leave synthetic division for your grade 12 teacher. Okay, that's one of the things I wanted to talk about today. Another one I wanted to talk about today is, and again, I kind of went through this a little bit with this group, but the group at home didn't get to see this. You guys should know very well how to factor a difference of squares, right? It's just x plus y, x minus y. You did this for lots in grade 10, and it popped up again in grade 11. What you don't necessarily know from curriculum is that there's a way to do, there's a way to do a difference of cubes the same way. And it works like this. You take the cube root of the two terms, you leave the sign between them the same, and then it's the square of this term, you change the sign between them, you times the two terms together, and then you square the last term. And that works even if there's coefficients here and here, as long as those coefficients are perfect cubes. So say you had one like, and I'm probably making up one from the homework, say you had 8x cubed minus 27y cubed. So according to my new difference of cubes work here, the cube root of 8x cubed is 2x. The cube root of 27y cubed is 3y. There's a minus between them. And then, okay, feel free to write this down in words if you want. Square the first, change the sign, times the two terms together, and square the last. And then, of course, you try to see, can I actually factor this? Oh, thank you, I missed the squared. Good eye. So there we go. And what's neat about this is this actually works for sums as well, right? There's no way to actually factor a difference of or a sum of, oops, that's an x. There's no way to factor an actual sum of squares. If somebody says, how do you factor that? You say, can't. That's like your grade 5 teacher saying, hey, make a factor tree for 17. You'd say, can't. It's done. 17. Factor this. Can't. It's done. But you can actually do the same thing here if this was a plus. If that was a plus, that's a plus, and that's a minus, and it's still the same answer. If you don't believe it, feel free to multiply this out. You can kind of see it. Multiply this out. You can kind of see it if you kind of think, because 2x times this number and 3y times that number are going to be terms that cancel. If you don't believe it, work it out and try it. Okay, the other thing you have, we only have a few minutes left here. The other thing that I handed you, besides the booklet with all this kind of grade 11, 12 skill practice, was I handed you out a booklet of function notation. Notice I already kind of talked about function notation today. It comes up in pretty much every aspect of what we do in this course. So I handed out this little handout. You can read it yourself. I don't have to read through it with you. But just keep in mind what function notation means. In grade 10, they probably just talked about how, oh, well, a function just means that instead of saying y equals 2x plus 3, you can just say the function of x is 2x plus 3. And you just kind of equate in your head, oh yeah, f of x just means the same thing as y. And that's true functionally, but it's a little deeper than that. When you think about this, at the end of the day, that's really only one variable, right? You have an x, and you have a rule that you do to x. That rule is I take every x coordinate, or every x number, I double it, and I add 3. So I don't even have to think about another variable, unless I was actually going to put it on a grid, and then I go, oh, well, the resulting numbers are going to go up, and the original numbers are going to go across. Hence, I'm going to have a grid that's x this way and f of x that way. And once again, you're probably going, well, that's just thinking like x and y. But this allows me to just think of it as one variable, and that's actually quite powerful when you're doing calculus, because calculus with two variables is a whole big difference harder than calculus with single variable. We actually do a little bit of calculus with two variables later in the course, but we start out by thinking about everything as a function. So how is your work with function notation? When I say, like it has here in this example, that f of x, actually I won't do your homework for you, I'll make up a new example. Suppose I have f of x equals x squared minus, or plus 3, and I want to know what f of 2 is. What is that asking me? Well, it's really kind of asking me, well, what would the y value be if x was 2? Right? If I plugged in a 2 for x, The 2 is the x coordinate on my grid. What's the y coordinate? So 2 squared plus 3 is 7. So there you go. F of 2 is 7. But what if I wanted f of 2? You might have done a little bit of this in grade 10. What does that mean? It means, well, I know f of 2 is 7, so I actually want to know what f of 7 is. So in other words, I take the output and I put it back into the input again. So quick, what's f of 7? I don't know. It's 7 squared plus 3, which is 49, and 3 is 52. What if I just wanted to know what f, come on, pen. What if I just wanted to know what f of x was? I don't even want a number. I just want an expression that means f of x. Well, let's see. What was f of x again? F of x was x squared plus 3. So I would like to put f of x into x. So I want x squared plus 3 squared plus 3. Got it? I replace the variable with the thing I'm telling you the variable is. And that's going to be x to the 4 plus 6x squared plus 9 plus 3 is plus 12. So this page here gets you thinking about plugging in f of x's, or plugging in values to f of x. On my blog, I put an actual answer key to this page, so you can try those. And then you can kind of keep working on the other thing. And that's as far as we're going to go today. So I'll shut off the video here. And if anybody has any questions, if anybody's tried any questions so far and they're stuck, we have a couple minutes we can take questions, right? In 4 minutes, band people got to go. Guys at home, you can ask questions too. But I'm going to stop the recording.